Okay, in this video I'm gonna show you how you could use Mohr Circle and formulas to find principal stresses, which is essential part of failure analysis in machine design. So to do that, I'm gonna consider an example here. So let's say we have element, a 2D element, which is under plane stress condition with this, consider this x-axis, y-axis. The normal stress on x-axis, let's say is 0, and then I have here shear stress of 1096, and then here I'm gonna have shear stress like that. Alright, and then on y-axis I have a normal stress of sigma y 8.84 KSI. So we are interested in finding our principal stresses and the orientation of our principal axes. I'm gonna show you three approaches. One is based on the formula you have learned in 209 and 309, and then I'm gonna show you how to use Mohr Circle to find our principal stresses. And then at the end, I'm going to show you that matrix approach, a matrix approach to find principal stresses and principal axes. All right, so using the formulas you have for plane stress condition, you know that principal stresses on a plane, if I consider 1 and 2, two principal stresses in my plane. Here is the formula you have seen. Plus or minus sigma x plus sigma y divided by 2 plus or minus sigma x minus sigma y divided by 2 plus tau xy squared. So plugging numbers into this formula is going to give you your first principal stress and second principal stress on plane xy, on the plane of xy. Please note that in general, all problems are 3D, so we have z-axis as well, but right now we are focused on axes x and y only, the plane of x and y, because we have plane stress condition. But you should always keep this in mind that we have also z-axis. For z-axis, since we are considering plane stress condition right now, sigma z is 0. So basically, for planar stress, you also have tau yz and tau zx equal to 0. So basically, the third principal stress that I have is 0, right? So we should keep this always in mind that all problems are 3D, and in 3D, we have three principal stresses. But when you have plane stress condition, one of your principal stresses, we know readily that it's 0. So the other two on plane xy, you can use this formula to find them. So let's see how we can put numbers here to find those. All right, sigma x is 0, sigma y is tension 8.84, it's positive, divided by 2 plus and minus, then 8.84 minus 0 divided by 2 squared plus tau xy is 7.96 KSI squared. So this gives me my two principal stresses equal to 13.52 KSI, and the other one is negative 4.68 KSI. All right, for failure analysis, you guys remember that from 209 that the failure theories are organized based on three principal stresses. So we always use those formulas, failure theories, we need to sort the stresses like this. Sigma 1p, which is larger than sigma 2p, and then that one is larger than the third one. So if you want to sort my principal stresses for this case, as you see here, my sigma 1p is going to be 13.52. The second one is going to be 0. The last one is going to be negative 4.68 KSI. So these are my three principal stresses. So the next question I need to answer is, what would be the orientation of the principal axis? So sometimes you are interested in that. So the equation we had in class, you have seen, is this. Tau xy divided by sigma x minus sigma y. All right. So here, when you use this, you have to be careful about the sign of sigma x, tau xy, because tau xy in this formula is positive when you have your shear stress. If you look at this figure, this is my tau xy. This tau xy is positive because, as you see, it's along y-axis. So first index shows the plane on which this shear stress is acting. The second index shows me the axis that this shear stress is parallel to. So if you see this shear stress is parallel to y and it agrees, its direction agrees with y, so it's going to be positive when I plug that into this formula. So my tau xy is, let me plug that into here, 2 times of 7.96 divided by my sigma x is, 0. The second one, sigma y, is 8.84. So from here you see that the angle is going to be negative because I have here negative. All right, from here theta p will be negative 30.47. All right, so if you want to find the orientation of my principal axis, one of them is going to be, okay, this is like my angle. So my angle is negative 30.5 degrees. So one of them is going to be like that, the orientation. The other one is going to be perpendicular to that, right? So you always know that the principal axes are going to be perpendicular to each other. So if you put this angle into transformation areas, you will see that the stress on here, on this plane, on this axis, is going to be, and this is going to be negative 4.8468. On this one, it's going to be 13.52. So basically, this is going to be my, the third, what I call here, the third principal stress, right? And this one is going to be my first one, so 1p. All right, so this is my orientation of my principal axes, and I found their magnitude as well using the formula. Okay, so to find principal axes, principal stresses, you use this formula, and for angle, you use this formula. So if you ask me what is the stress, let's say this is my original x and y axis. Let's say I change my x-axis to this x prime, this angle is theta, this one is y prime. Then sigma x prime will be sigma x prime. The stress transformation equation will be, I had this reviewed for you in class. You learned about this, and again, 209 and 309, these are the equations we had. So for if your x-axis rotated gets rotated to x prime and you get to x prime with theta rotation of rotation angle of theta, sigma x prime and sigma y prime, you can calculate them using these two formulas. And tau x prime y prime, you can find it like that. So if you're interested in stress, value of stress in other direction, this is how you guys can calculate that. But most of the time, we are interested in principal axes and principal stresses. So I showed that to you how to use the formulas to find those for plane stress condition. All right, so next I'm going to try to use Mohr circle to do the same thing. So for Mohr circle, I have, okay, let me draw my state of stress. I have here 7.96 KSI, and then this one is 8.84, and here sigma x was 0, sigma y was this. All right, so to do Mohr circle, you guys know that when you want to do Mohr circle, you will have a circle like this. The center of the circle, you can always find it looking at this. It's like average stress. And then what is the radius? Basically, this is the radius. Squared plus tau xy squared. This is the radius. All right, so each coordinate system, each setup, each configuration of x and y coordinate actually are gonna, each axis is gonna be represented by a point, a single point on this circle. So once you have C and once you have R, you can build your circle. So the next question is where those two axes, x and y, are located on my Mohr circle. All right. So the way we do that, we have to find coordinates of x and y. So x-axis coordinate on the Mohr circle is going to be like that. My normal stress is 0. My tau xy, this is the magnitude. But you have to be careful here. When it comes to Mohr circle, our convention is a bit different from what we have done in other parts of 309 and 209, or even trigonometry. When your shear stress is rotating, if you consider internal point on the element, if shear stress is rotating counterclockwise about the internal point, we consider that as negative shear stress on Mohr circle. So this will be actually on the x-axis, you see here. My shear stress that I need to consider is going to be negative. The other one, on y-axis, you have 8.84 for your normal stress. Shear stress, if you had here negative, on the other side it's going to be positive. So this comes on Mohr circle like that. For x-axis, my normal stress is 0, and then my normal stress, so it looks like I have to move this, my y-axis. So you guys know that in this coordinate system, when we have our Mohr circle, x-axis is going to show us normal stress as x and y, and here you're going to have tau xy. So x point on the Mohr circle is going to be here. Your normal stress is 0. Your shear stress is negative 7.96. And if you connect that to center and then extend it, the other side is going to show me my y-axis. So my y-axis is the normal stress is 8.84, and the shear stress is now positive 7.96 KSI. So this is the Mohr circle for this problem, all right? So as I said, x-axis is gonna show me my normal stress, y-axis is gonna show me tau xy, all right? So if you ask me this question, what would be, if you ask me that what would be my normal stress and shear stress if I rotated x-axis counterclockwise with angle theta? So this is again similar problem we try to do it using formula. So if this is x and y, I want to rotate x and y like this counterclockwise to get x prime and y prime with angle theta. Then the question is, what would be normal stress for x prime? What would be normal stress for y prime? All right? So to do that, on Mohr circle, you have to locate first x-axis, which is here. To get to x prime on the element, I have to rotate counterclockwise with theta. On the Mohr circle, you have to rotate x same direction. You have to move same direction, but with angle twice as much as theta. So I'm going to get actually like this. All right, so if I rotate like this with 2 theta, then you see here on the element, if I rotate with theta, I'm get to x prime. On the Mohr circle, if I rotate 2 theta, you get to x prime. And so if you ask me for this point, what would be the shear stress or normal stress? I projected on x-axis. This will be your sigma x prime. And on y-axis, if you project it here, you're going to get your tau x prime y prime here. This length, this corner, which is negative. If it is negative, it means that it's actually counterclockwise. All right, so if I want to plot my stress for x prime, y prime, you see that x prime is going to be positive sigma x prime, so it's going to be like tension. I'm not going to try to find the value, but the shear stress, you see it's negative still for tau x prime, y prime. So it means that it's going to rotate counterclockwise. So this is my tau x prime, y prime. And then I have y prime. So, so if you ask me what would be the normal stress acting on x, I have to connect x prime to center and then extend it to get to y prime. And then if you project it on x-axis, this distance from the center, from the origin to this point is going to give me sigma y prime. And then this is my tau xy, tau x prime y prime, which is equal to what I had here, okay? So this is how you find stresses on new coordinates, new axes, when you rotate your original axis using Mohr circle. Okay, but more important question is, what would be my principal stresses using Mohr circle? You see here, at this point, I'm going to have farthest distance from the origin of my coordinates. So this is going to be my sigma 1p, one of my principal stresses. The other one is going to be here, right? So how you find that sigma p, 1p? Basically, that is your center plus your radius, right? So if you find these two guys, your radius, using the numbers I have here, radius is 9.10 KSI. Your center is 4.42 KSI. So I have these two guys. Sigma 1p will be center plus r. If you add these two, you're going to get 13.52. Okay, let's say it's 13.5 KSI. And sigma, the other principal stress here, I know that my second principal stress from z-axis, I know it's already 0. So this one will be my third one. So third principal stress for this problem is going to be C minus R, which is basically what I had before. All right, negative 4.68. So we found these two, and we had this. So using Mohr Circle, this is how you find your principal stresses. Next question is how to get the orientation of my principal axis. So let me have this, draw this again cleaner. All right, so this is kind of my sigma x, sigma y, tau xy. All right, so this was my x-axis, this was my y-axis. All right, so x-axis, the coordinate was 0 and negative 7.96. And this one is 8.84 and 7.96. All right, so looking at here, you see this was my first principal axis, this one. Technically on xy coordinate, this is my second principal axis, but for this problem, this is my third one. Let me consider the third one. All right, so if I rotate y-axis with this angle, if I call it 2 theta p, 2 theta, let's call it 2 theta. If I rotate it with this angle, I'm going to get to 1p. All right, so let's see how we can find this angle. This angle, basically, if you build a right triangle here, sine of that 2 theta equals what? Equals your shear stress, your opposite, divided by this, your radius, which is, I had the radius to be 9.1. Okay, so 2 theta, okay, let's say theta will be, I should go arc sine of this and then divide that number by 2 to find my theta. So let me use my calculator to show you. All right, so let me turn off this light. See if you can see it better. All right, arc sine of okay, arc sine of 7.96 divided by 9.10. This is my angle, right? Divided by 2. This is my 2 theta, but the theta is going to be 30.5. So theta is 30.5. This is what I had before. So this means that, okay, let's look at the orientation. This was my x, this was my y. So from Mohr Circle, you guys see that if I rotate y in clockwise direction with 60 degrees, I'm going to get to sigma 1p. On the actual element, this means that I have to rotate y in clockwise direction, half of that angle, which is 30.5, to get to my sigma 1p. So this is going to be my 1p. And so that is going to be my 2p, my second principal axis on this plane. If you look at here, if I keep rotating, after I rotated 2 theta, if I keep rotating more, right, so 180 degrees, right, on Mohr Circle. So if I keep rotating 180, I'm going to get to my other principal axis. 180 on Mohr Circle means 90, so 1p rotated clockwise 90 degrees, so you get to my other principal axis. All right, so these are going to be my orientation of my my stresses. I'm sorry, my principal axis using Mohr Circle. We got same thing, right? So here, if I had to rotate y in 30 degrees, 30.5. This means that your x-axis actually has rotated has to rotate 30 degrees clockwise direction to get to my other principal axis. This is what we had from the formula, all right? But I like Mohr Circle better because with one look, you can see how the stresses are gonna vary, get the whole picture, how stress is gonna vary on that element in different directions, principal axis, maximum shear stress, everything. It's gonna tell me everything about the element. You know, for some angles, you see my normal stresses are gonna get negative, and when you have it positive, and all other information you learn from here. All right. So this was Mohr Circle. Last approach I would like to show you guys is the method based on matrix operation. If you guys took linear algebra, you learn about matrices and how to find eigenvalues and eigenvectors. And so I'm going to show you how we can actually find principal stresses using the eigenvalues and eigenvectors of matrix. We can put stresses in this form, into a matrix. And in mechanics, we call this matrix actually tensor. If you look at the books, they no longer call this